Welcome to this 6th lecture in this course on fluid mechanics for chemical engineering undergraduate students. In the last lecture, we were discussing fluid statics, that is, the forces that are present in a fluid that is not under any kind of motion, that is, the fluid is static, and we will see that there are some interesting features that come about even in a static fluid, and that will be the subject of our discussion for this lecture. If you recall, forces in fluids can be classified into two types. Okay. We divided them into broadly as body forces and surface forces. Okay. So, if you remember, we are carrying out all our analysis within the continuum framework, where the fluid is assumed to be a continuous medium in which various quantities such as pressure, density, temperature, velocity, they are all assumed to be smoothly varying functions of both spatial and time coordinates. So, within the continuum framework, if you consider an element of fluid, for simplicity I take a volume element which is cubic in shape. Okay, this is a volume element in a fluid. Okay. We can ask the question, why is this volume element in general going to move if the fluid is not under static conditions? Well, it will move because of the fact that if you apply Newton's laws of motion, so mass times acceleration of this volume element is equal to sum of all the forces in the volume element. If there is an imbalance of all the kinds of forces that are present in the volume element, then the fluid element will accelerate. So, it is important to know what are the forces that are acting. So, one force that is known to us is called the body force. Okay. The body force acts entirely through the entire volume of the fluid. Okay. Well known example is that of gravitational force. Suppose you have this volume element, the volume of the volume element to be delta V, then the mass of this volume element is rho times delta V, okay, times the acceleration due to gravity g, okay, will give you acceleration as a vector. So, will give you a body force that acts through the entire element of the fluid, entire volume of the fluid. So, these are called body forces, or sometimes these are also referred to as volume forces. Okay. In contrast, surface forces are forces that are acted upon only on the surfaces. Okay. For example, if you consider the top surface of this cubic volume element, the fluid that is present just immediately outside will exert a force on this surface, okay, and this is called a surface force. The nature of the surface force is ultimately due to molecular interactions. Okay. For example, if you consider a very dilute gas, okay, if you consider a tiny volume element within the gas, then the gas molecules present outside will be colliding with these molecules present inside, and that will result in a force, and that force will just be present only on the surface. It won't extend into the interior of the volume elements. So, since these forces act only on the surface of the given volume element, they are called surface forces. Okay. And the surface forces in general, okay. So, let us discuss a little bit more about surface forces before going to static fluids. Okay. If I take a very simple surface element, okay, this surface element, there is fluid present outside. So, the surface element forms part of a volume element, which is the cubic volume element that we have chosen for simplicity. But let us consider one of the surfaces, namely the top surface. There is fluid present outside and there is fluid present inside. Okay. And every surface is marked by a normal, the unit outward normal, let us call it n. So, n is the unit outward normal to the surface, outward normal. It is a unit normal perpendicular to the surface, and it is pointing from inside to outside, therefore, it is called unit outward normal. Okay. Now, if you consider the forces in general that are exerted by the fluid that is present outside on the fluid that is present inside on this surface, this force, which we will call R, can point out in general in any direction. Okay. This R is a function in general. Okay. It is a function of the surface on which we are focusing, that is the top surface. So, it is a function of the unit outward normal, but the direction of this force need not be always in the direction of n, it can be in any arbitrary direction. Okay. So, R is the force, but per unit area, R is a function of n. So, let us write this as R of n. R of n is the force per unit area acted upon by the fluid outside on the fluid inside at the surface. The inside and outside are demarcated by a surface. So, R is the force that is per unit area exerted by the fluid that is present outside on the fluid that is present inside. So, if you look at this surface of interest, okay, and let us say this is the unit normal, okay, this R can be resolved into a component that is parallel to the normal. Okay, let us call it Rn, and then it can also be resolved in the direction perpendicular to the normal. Let us call it Rt1, Rt2. Okay. Now, Rn is called the normal stress. It is the normal component of the force that is being exerted by the fluid outside on the fluid inside. Rn is called the normal stress, while Rt1 and Rt2 are called tangential or shear stresses. Okay. So, in general, the fluid that is present outside will exert a force on the fluid that is present inside only on the surface, and this is because of viscous action. Okay. And this force can have a component along the normal as well as a component perpendicular to the normal. Okay. But when we look at a static fluid by definition cannot bear any shear stress, because if there is any finite non-zero shear stress, the fluid will start moving. So, the shear stresses in a static fluid must be 0. So, the static fluid is a fluid where the shear stresses or the tangential component to the stresses are 0. So, the only, because otherwise a fluid will start moving, we are now considering a fluid that is completely stationary or static. So, if a fluid is stationary or static, if you take any volume element, okay, and inquire what is the forces on the surface, there cannot be any component that is parallel to the surface, because if there were to be a force that is parallel to the surface, then that will constitute to a shear force or shear stress, and the fluid will start moving. So, since we are considering only static fluids where there is no motion, okay, there cannot be any shear stresses. So, if you take a static fluid and if you take a volume element in a static fluid, okay, on each and every surface the force can exert only purely normally. Okay. If you take a static fluid, okay, and you take a volume element that is big, okay, then regardless of the nature of the volume element, okay, the force will act purely normally to the surface of the volume element. There cannot be any force that is tangential to the volume element. Okay. So, the shear stresses are 0 in a static fluid. Okay. Now, this need not, the result that shear stresses are 0 and the force is acting purely normal to the surfaces holds for any arbitrary volume. Suppose I take a very arbitrary volume. This is a 3-dimensional volume, but I can draw only a 2D sketch of it. Okay. The force is always in the direction of the normal for any arbitrary volume element in a static fluid. Okay. So, R of n in a static fluid must be, since R is a vector and it is purely in the direction of the normal, must be some constant times n, because R is purely in the direction of n, and so it must be some constant times n. So, R is a vector, n is a vector, this constant is a scalar constant, a scalar. So, in general, quantities of physical interest can be classified as scalars or vectors. Okay. Scalars are quantities which are described by a single value, numerical value at a given point in space. For example, if you say temperature at a point, it has only one value and it has no sense of direction at a given point in space in a fluid. Likewise, if you consider density, you can ascribe a value of density to a point in a fluid within a continuum hypothesis, but there is no sense of direction associated with density. Okay. So, whereas quantities such as forces and velocities are vectors which have a magnitude, that is a numerical value, as well as a sense of direction at a given point in fluid. Okay. So, this constant C is a scalar. So, if you take a surface area delta A in a static fluid, okay, and you ask what is R, the force exerted by fluid that is present outside on the fluid that is present inside, it has to be in the direction of the n. It has to be purely normal to the area element, surface element. Okay. Usually, it turns out that this normal force in a static fluid is compressive. That is, the force is acting inwards, okay, while the unit normal n is pointing outwards, the force is pointing in the direction of minus n. Okay. So, R of n is normally written as minus a constant, a scalar P times n, where this P is called the pressure. So, pressure is the magnitude of the compressive force that is exerted by the fluid that is outside on the fluid that is inside. Okay. And since R of n is proportional to n and n is pointing outside and P is compressive, this negative sign accounts for this compressive nature of this force or stress in a static fluid. So, this is called the pressure. Okay. So, the pressure is denoted by the letter P, is the normal force, normal compressive force per unit area acting in a static fluid. Okay. We can also, well, before I proceed further, the units of pressure is newtons per meter squared is 1 Pascal. SI, in SI system, units is P is 1 Newton per meter squared is 1 Pascal. Okay. That is a standard units. Okay. We also showed in the last lecture that suppose I take a point in a fluid, okay, a point in a fluid, and I construct a tiny volume element about that point, okay, infinitesimal. Suppose I take an infinitesimal volume element about a point, and then I ask the question, what is the value of pressure? So, this, for simplicity, this volume element is again a cubic volume element. So, there are 8 faces, there are 6 faces to this cube. Okay. There are 4 side faces and top and bottom. There are 6 faces to this cube. So, you can ask the question, the pressure will act purely normally, okay, in all these 6 faces, but what is the value of the pressure P, okay, as the volume element shrinks to 0, Okay. So, the question is, we know that pressure will act purely normally at each and every phase in a static fluid, but what is the value of P? Is it same or it is different along the different phases? We are going to show that it is in fact the same. Okay. So, in order to do this, we take a wedge like volume element. Okay. We take a wedge like volume element. Okay. And let us put a coordinate system. This is x and y is going into the board and z is okay. So, y is the direction that is in the plane perpendicular to the board. Okay. So, since and let us call the dimension perpendicular to the board as b, and let us call this dimension as delta z, and let us call this dimension as delta x, and let us say there is a body force of gravity, acceleration due to gravity g acting. Okay. And let us call this top dimension as delta s. Okay. So, since this b is very large compared to the thicknesses delta z and delta x, we need not consider any variation in the z direction, sorry, in the y direction, in the plane perpendicular to the board. Okay. So, now first we will ask what are the various forces in order to prove that pressure. Okay. So, let us give some notation. Let us call this P z. This is the pressure that is acting on a surface which is whose perpendicular is in the z direction. Let us call this P x. This is the pressure acting on a surface whose perpendicular unit normal is in the x direction, and let us call this on the pressure on the inclined surface as P n. Okay. So, let us call this as theta, angle theta. This is also angle theta by geometry. Okay. So, what are the various forces? Well, firstly, what is the body force acting on this wedge like volume element? The body force is the mass times acceleration due to gravity. Mass is nothing but the density times volume. Volume of this wedge, suppose you consider a rectangle, okay, a cubic volume, and then you divide it into half through the diagonal, okay, and then it is a volume element in the third direction like this. Okay. So, the volume of this is half the volume of this rectangle. So, I will put half delta x delta z times b times g. Okay. This is the mass times acceleration due to gravity g. Okay. This is the body force that is acting on this wedge like volume element. What are the surface forces? So, in order to do this, I will just consider a cross section of this wedge like volume element. I will take a cut in the y direction, and this is P x, this is P z, this is P n, and this angle is theta, so is this angle. Okay. So, this P n will have component in the horizontal and vertical direction. Okay. So, what are the various forces acting on this static fluid element? This fluid element is static. Okay. So, what are the various forces? Okay. Let us take the x component of the force. Okay. Let us take the x component. So, just to remind you, we had x like this and z like this. Okay. The x component of the force is the acceleration due to gravity is acting purely in the minus z direction. So, the x component of the force balance will tell us that on this face, okay, the force is the pressure times the area of the face, which is nothing but delta x, okay, sorry, delta z times b, okay, and minus this is acting in the plus x direction, but there is also a force due to this force which is acting normally to this inclined surface. It will have a component in the horizontal direction or x direction, which is nothing but P n. Okay. So, the area of this face is delta s times b, and the force has a component P n sin theta. Okay. If this surface is completely vertical, that is theta is pi by 2, the normal force will be purely P n, but this surface is inclined. So, there will be a component of this surface of this force on this in the x direction, which is P n sin theta. So, the sum of forces must be 0, because by Newton's second law the fluid is static. So, sum of all the forces must be 0. So, likewise the z component, but before I do that I can simplify this further. So, just from geometry, delta s sin theta. So, we have this is delta s, this is theta, this is delta z, that is delta x. Okay. Sin theta is nothing but delta z by delta s. So, which implies delta s sin theta is delta z. So, instead of this delta s sin theta, I will put delta z. Okay. Then this equation will tell me that delta z b will cancel with this delta z and b. So, this will imply that, okay, p n minus p n is 0, or p x is equal to p n. Okay. So, likewise we can do a similar thing for the y direction. Okay. In the y direction, again we look at forces. So, the forces will be, so the force on this face is p z, okay, it's p z times delta x times b, okay, that is the force in the plus y direction, and there is a force, the component of the force on the inclined surface, that will be p n cosine theta, that will be acting in the minus z direction. So, will be minus p n cos theta times delta s times b. Also we have the acceleration due to gravity, the body force acting in this direction, which is minus rho half b delta x, sorry, half b delta x delta z times g, okay, and sum of all this must be 0. Now, just by geometry, delta s cos theta is nothing but delta x. Okay. So, I can cancel delta x right through the equation. Okay. So, I get, and then I can cancel b right through the equation. Okay. So, I get p z minus p n is equal to half rho g delta z. Okay. And in the limit as delta z shrinks to 0, we get p z is p n, but we also showed p x is p n. So, p z is p n is p x. So, if I take a surface like this, if I take a point and then I construct a volume element like this, which is extending in the third direction, which will not worry, the pressure is acting in a static fluid as this volume element shrinks to 0. The pressure acting on these faces with different orientations, they are the same. The magnitude of this force per unit area is exactly the same. Okay. So, the pressure, so what we find is that you take a point, if you take a large enough volume, a macroscopic volume in a static fluid, the pressure will be purely normal to this arbitrary volume element. Okay. Okay. But as I shrink this volume element to a tiny point, then the value of the pressure will be the same. It is purely normal to the surface of this tiny volume element, but as this volume element gets shrunk to a point, even the magnitude of the pressure, the numerical magnitude will be the same, and it is independent of the direction of the orientation of the surface. Okay. Now, the next task for us is to find what is the pressure force on a fluid element. Okay. In order to do this, we will take a simple volume element again, take a cubic volume element. Okay. And I will put coordinate system x, y and z, okay, along the 3 directions, and I will call this as delta y, or okay, and this as delta x, and this width as delta z. Okay. Now, let us also put some labels for the phases. Let us call this phase A, B, C, D. Let us call this phase E, F, G, H. Okay. So, we want to find out what is the pressure force if this volume element is surrounded by fluid and it is exerting a pressure under static conditions. What is the pressure force, net pressure force acting on this fluid element? Okay. To answer this, pressure on the phase, or force to be precise, force on the phase ABCD. ABCD is this phase, okay, is nothing but, okay, P of y. So, this pressure in general will be different from this point to this point. Okay. Since this is a tiny volume element, the pressure at a given phase is essentially the same, but its value will change from one point to another. Okay. Times the area of this element. The area of this element is nothing but delta z times delta x. So, this is the force, okay, acting on the phase ABCD. The force on the phase EFGH is nothing but, in general the pressure will vary from this point to this point. So, we write this as P of y plus delta y times delta z times delta x. Okay. Now, we are going to consider infinitesimal tiny volume elements. For infinitesimal volume elements, that is as delta y, delta x, delta z tend to 0, we can always write by what is called a Taylor series P of y plus delta y is nothing but P at y plus partial P by partial y times delta y plus half partial squared P partial y squared delta y squared plus so on. Typically, these higher order terms are smaller, so we can neglect, and we can keep our expansion only up to first order. Okay. So, if such is the case, then the force, the net pressure force in the x direction on the volume element is given by nothing but, we have to worry about the force on the phase ABCD and the force on the phase EFGH. Okay. So, this is P. So, the net pressure force acting in the y direction, because remember this is x, this is y, this is z. Okay. dFpy, this is the net pressure force, the y component of the net pressure force. So, I am sorry, this is the y direction, is nothing but P at y times delta x delta z minus P at y plus delta y times delta x delta z. But I can use the Taylor series expansion to write this as P at y minus P at y minus partial P partial y times delta y times delta x delta z. So, these will cancel to give dFpy is nothing but minus partial P partial y times delta x delta y delta z. This is nothing but the volume of the cubic element. So, I can write is minus partial P partial y times delta v. Okay. So, similarly, so what we have done is, just to recapitulate, if you take a volume element, a cubic volume element with x, y and z like this. Okay. The net y component. So, let me just go back and correct any problems with notation. So, we are there still doing it in, yeah. So, that is perfectly fine. So, the net force, okay, in the y direction on this fluid element is due to the pressure acted upon by the fluid that is present outside on the fluid inside is this. This is the y component, but just by analogy, similarly you can do it as an exercise at home. You can show that dFpx, the net x component of the force due to pressure alone, is minus partial p partial x delta v, and dFpz is minus partial p partial z times delta v. Okay. So, we can construct the vector force. Okay. So, if you have three components of a vector, suppose I have a vector f and I have three components fx, fy, fz, I can simply reconstruct this in the Cartesian coordinate system as fx times I plus fy times j plus fz times k, where I, j, k are the unit vectors in the x, y and z direction. So, dFp can be simply written as dFpx I plus dFpy j plus dFpz times k, where I, j, k are the three unit vectors along the x, y and z coordinates of the Cartesian coordinate system. Okay. So, I can substitute for dFpx minus partial p partial x I minus partial p partial y j minus partial p partial z k times delta v. Okay. So, for those of you who have taken elementary courses in mathematics, engineering mathematics, where you would be dealing with vector calculus, you would recognize that this is nothing but what is called the gradient of p. Okay. I will just take a couple of minutes for those who are not familiar with this concept. So, gradient of a scalar quantity, what does it mean physically? Okay. So, let me just take 2 minutes to explain this before I discuss the physical significance of the result that we have just derived. So, let me just rewrite this. dFp is minus del p times del v. Okay. So, what do you mean by gradient of a scalar? Okay. Suppose I have a function that is function of only one variable f of x. Okay. Now, if I want to know, if I change the value of x by an amount dx, okay, then the function f will change. The delta f is the change that is obtained by the function, that is incurred in the function as you change x by delta x, is from definitions of calculus df dx times delta x. As the value of delta x becomes small and small, the change in the value of the function, suppose I have a function f versus x and I take a tiny element x of length dx, this change, okay, this is the change that is incurred by the function delta f. This change is nothing but the slope at that point times the value of the displacement you are doing. Okay. So, this is true for normal functions, but suppose you have a function that is not a function of single variable, it is a function of 3 variables, not just one variable, where the 3 variables are the 3 coordinates directions in Cartesian coordinate system. Then how do you think of delta f? What is the change in the function f? So, if you consider a function not just of one variable, but 3 variables, and you ask the question, what is the change incurred in the function as you proceed by a small distance dx, but x is no longer a scalar, it is a vector, because you can undergo a displacement in the 3 coordinate directions dx times I times dy times j plus dz times k. Then what is the value the change in the value of the function f. Okay. It turns out that gradient of the function has that information. So, gradient of a function. Okay. So, if f is a function of x, y, z, okay, then if x changes by a small amount delta x, y changes by a small amount delta y, z changes by a small amount delta z, then df is nothing but partial f by partial x times delta x, keeping y z constant, partial f by partial y constant x z times dy del y, plus partial f by partial z x y delta z. Okay. So, this can also be thought of as df, the change in the value of the function. This, the displacement vector that we have undergone is delta x I plus delta y j plus delta z k. So, I can also rewrite this as a quantity which is a vector, which is nothing but partial f partial x I plus partial f partial y j plus partial f partial z k dotted, this is the dot product in vectors, with delta x I plus delta y j plus delta z k. Okay. This is nothing but the displacement vector that we have undergone, okay, dx. This quantity is identified as grad f, okay, dotted with dx. This is df. So, this quantity is called the gradient of the function f. Okay. So, the gradient of the function gives you information about the changes a function encounters as you suppose you have x, y, z coordinate system and you are traversing any arbitrary distance delta dx. Okay. The gradient of the function has the information as to how much this function f will change, that is df, okay, as you undergo a vectorial displacement dx about a point. Okay. So, the expression that we derived, now going back to static fluids, the expression that we derived is that the force acting on a fluid element is minus partial p partial x I plus partial p partial y j plus partial p partial z k times delta v. This is nothing but minus grad p times delta v, okay, dfp. So, this force that is acting on a tiny volume element, recall that our volume element is cubic in shape, okay, is proportional to the volume of the volume element, and therefore, I can define a force density, that is small f p, that is force, differential force acting on this volume element divided by the volume, is nothing but grad p. Okay. So, there will be a net force on this volume element only if there is a change or variation in pressure. So, if each phase has the same pressure, then obviously all these forces will cancel out. So, there will not be a net force due to pressure variation, because there is no variation in pressure, therefore, the forces will cancel out, giving rise to no net force. But if for some reason there is a pressure variation in a volume element, then that will give rise to a net force on this volume element. Okay. So, this is called this is the net force acting on a volume element due to pressure. Okay. So, one can make a very simple corollary. So, if net forces, if the net force acting on a volume element is proportional to grad of p or the gradient of pressure, that means that if there is a constant pressure acting everywhere, okay, on a volume element, that will not give rise to any net force. A constant pressure acting all around a volume element will not result in a net force. Okay. Why is this important? This is important because in many practical applications, in terrestrial applications, there is a constant atmospheric pressure that is acted upon by the air that is present, and this constant atmospheric pressure will not cause a net force on many problems of interest in fluid statics and fluid flow. Okay. So, this force, this pressure is called the atmospheric pressure. This is the pressure due to the air that is present in the atmosphere. Due to so, this is called the atmospheric pressure, commonly denoted as P atmosphere. So, if you measure the pressure P of a fluid, then that is called the absolute pressure. This is the actual pressure that is present in the fluid. But since if you in many problems you have atmospheric pressure acting all around, it is only the difference between the atmospheric absolute pressure and atmospheric pressure that matters. So, this is called the gauge pressure. Okay. So, this is if the pressure in the fluid is greater than atmospheric pressure. If it is less, then the reverse of it is called the vacuum pressure. If P is less than P. This definition just ensures that vacuum pressure is a positive quantity. Okay. So, an uniform pressure acting all around a body will not result in a net force. Now, let us worry about if you consider a volume element like this, cubic volume element. We know that, so let us put coordinate system x, y and z. We know that the forces due to pressure, the force per unit volume due to pressure is, the net force per unit volume due to pressure is minus delta p, and the net force per unit volume due to gravity is simply rho g. Okay. So, if this fluid element is static, then the sum of all forces on this volume element must add to 0, which implies that minus delta p times rho delta v plus delta v rho g must also be equal to 0. So, if I cancel delta v right through, we get minus delta p plus rho g equal to 0. This is the fundamental equation of hydrostatics. This is the fundamental equation of hydrostatics. Okay. Minus delta p plus rho g is 0. This is a vectorial equation. Any vectorial equation can be written in its 3 component form. So, this will have 3 forms, 3 components, minus dp dx plus rho gx is the component of the acceleration due to gravity vector in the x direction, minus dp dy plus rho gy is 0, minus dp dz plus rho gz is 0. Okay. So, it is traditional or conventional in fluid flow to align the gravity vector vertically along with one of the coordinate axes. So, suppose I call this x, y and z, okay, and the 3 unit vectors are I, j and k, okay, and gravity is acting downwards. So, g, the vector g is written as minus or g times minus k. Okay. So, that means that g x is 0, g y is 0, g z is minus g. Okay. So, one can simplify these equations to write as partial p partial x is 0. I am sorry, all these are partial derivatives because we are looking at variations in all the 3 directions. So, you have partial derivatives. okay. Partial p partial y is 0. There is no variation in the pressure in the x direction, no variation in the pressure in the y direction, but in the z direction partial p partial z will go as minus rho g, because g z is minus g. So, if I take this to the other side, I will get minus rho g. Okay. This is a fundamental equation. This is a fundamental result in hydrostatics. If you place the gravity vector in the minus k direction, then pressure is independent of x and y direction, and it is a function only of the z direction, and the way in which it is going to vary is this. So, what are the assumptions of this when this equation is valid? This is a very important equation. This is valid for static fluid, okay, and the gravity is aligned along the minus k direction, okay, and the gravity is the only body force. There can be other body forces in general, but just in this introductory discussion we keep things simple. So, we take gravity to be the only body force. Okay. Now, can we solve this, or can we simplify this further? So, you have minus partial p partial z is rho g. In order to integrate this, we need to know whether rho and g are functions of z or not. G is practically a constant in terrestrial applications and most engineering situations. So, g is a constant. So, the next thing is rho a constant or not? Is it a constant? Okay. Well, it depends on context to context. In many fluid flow problems, the fluid can be considered to be incompressible. That is, rho is independent of the pressure. There is no change in the density because of the fact that the pressure in the fluid is changing. So, rho is considered to be independent of pressure, then the fluid is incompressible. Okay. And rho is independent of, and rho is a constant. Okay. So, if you consider the density to be constant, then this equation can be integrated in a straightforward way. So, you write minus integral z1, or rather if I integrate, if I take 2 points in the fluid where the elevation is, or the height is z naught and z, and where z is z naught, p is p naught, and where the vertical coordinate is z, pressure is p, then I write minus integral p naught to p dp, okay, is minus rho g. Since rho is considered to be a constant for an incompressible fluid, I will integrate this from z naught to z dz. Okay. So, p minus p naught is minus rho g times z minus z naught, or is equal to rho g times z naught minus z. Okay. Now, usually what happens is we can, so the way we have done the problem is z is pointing like this and gravity is pointing in the opposite direction. Okay. Suppose you have trough of water, okay, and there is a free surface, this is let us say water, and here it is air, the pressure is atmospheric. Okay. Suppose you take z naught, okay, z equals z naught as the interface where the pressure is atmospheric. So, p naught is p atmosphere, and let us take z naught minus z as h. So, h is the depth from the free surface where the pressure is atmospheric. So, we can write p minus p atmosphere is essentially rho g h, okay, where z naught is the location where the pressure is atmospheric, and z is any arbitrary location. So, this is z, this is z naught minus z is denoted by the symbol h. So, which implies p is p atmosphere plus rho g h. This is a fundamental equation in hydrostatics. The pressure varies. So, if you consider the pressure here in the air to be atmospheric, and if you look at each and every point in the fluid as you go down in h, okay. So, this is z, okay. As z decreases, then the depth of the water increases, okay, from the free surface, then the pressure will increase compared to its atmospheric pressure due to the weight of the liquid column that is present above. This is, so if we take any H, okay, the weight of this liquid column will act to increase the pressure. So, this is the fundamental equation of hydrostatics in incompressible fluids, okay, and the pressure increases in an incompressible fluid because of the fact that the pressure at any point in the fluid has to, suppose you take if you take a force, if you take a cylindrical volume element and if you do a force balance, the pressure here is acting normally like this, the pressure here is atmospheric. The pressure here has to balance not just the atmospheric pressure, but also the weight of the fluid element that is present in between the two levels. Okay. So, this is a fundamental result in hydrostatics for incompressible fluids. Now, you must have seen or learnt of what is called a Pascal's law or Pascal's principle for incompressible fluid, which says that pressure applied to an enclosed liquid is transmitted undiminished to every portion in the liquid and to the walls. And to the walls of the container. Okay. So, where does this principle come from? This principle merely is a consequence of this relation, this equation. Okay. Suppose you consider a container in which you are imposing a pressure P naught, and this is, let us say, water, it is incompressible. Okay, there is liquid here. So, P at any, so this is gravity. So, P at any location is P naught plus rho g h. Okay. Suppose you change P naught, okay, to some other value. The change in pressure, okay, is because of change in P naught plus change in pressure at any depth h from the surface, okay, is delta P, and there is change in P naught, and then there is change in rho g h. But you are looking at the same h. So, this change in rho g h will amount to only change in h because there is rho is constant for an incompressible fluid, g is constant. So, rho g delta h, but you are looking at the same h. So, delta h is 0. So, this implies that the pressure that you apply, the change in pressure that you make at the surface here will transmit undiminished to each and every point in a static fluid. This is the Pascal's principle. Now, there are some other ways of integrating this equation. For example, you have dP dz is minus rho g. Okay. Now, we assumed initially the fluid to be incompressible. Now, let us say the fluid is not incompressible, but it is compressible, and when the fluid is compressible, the pressure and density are related through an equation of state. Let us assume the equation of state to be that of an ideal gas, where P V is given as number of mole times universal gas constant times T. Usually this is written as P is number of moles is mass divided by the molecular weight of the gas, okay, and I am bringing V down RT. So, m by V is the density and R by molecular weight is called the specific gas constant. So, let us call it Rg. This is not the universal gas constant, it is specific gas constant. So, P is rho Rgt. So, instead of writing rho g, I am going to, from this equation I am going to write dP dz is, instead of rho I am going to write P by Rgt, okay, is minus P by Rgt times g. Okay. So, this can be integrated. So, dP by P, okay, is nothing but minus g over Rgt dz. This is log P is minus g by Rgt, and the temperature is assumed to be a constant. Okay. So, here we are looking at an isothermal condition, but the temperature is fixed. Okay. The gas is at constant temperature. So, T is constant. Okay. So, you can integrate this just to give T is a constant. So, you can integrate this trivially to give z plus c. So, if you assume p is p naught at z is z naught, you can fix this constant. So, you get log p over p naught is minus g by r t naught. So, t is t naught, a constant, it is isothermal. Okay. So, times z, or p is p naught exponential minus g by r t naught times z. Okay. So, we can integrate this equation for statics, static fluids, not just with the incompressibility assumption. So, even if you assume the fluid to be compressible, but by supplying the ideal gas law, we got a simple relation for the variation of the pressure with the elevation. Okay. Now, this is for ideal gas, and P is P naught plus rho g h. Okay. This is for incompressible. Okay. Now, this expression can be simplified when g z by r t naught is much less than 1. Okay. If this is the case, when the elevations are not so high, then I can, when suppose you have e to the minus x, when x is small, okay, then I can write it as 1 minus x approximately. So, in the limit g z by r t 0 is small. So, this is the universal, it is the specific gas constant, which I denote by r g. So, p by p naught is written as 1 minus. So, since there is 1 minus g z by r g t 0. Okay. Now, p by or p is p naught minus p by r g t 0 g z, but from the ideal gas law p is rho r g t 0. Okay. So, p by r g t 0 is nothing but rho. So, p is p naught minus rho g z. Okay. So, this is the same equation that we obtained for incompressible fluids, okay, but this is obtained as a special case when g z by r g t 0 is very small compared to 1. So, even if you assume compressibility, when the elevations are not so large, this essentially boils down to the same linear variation of pressure with respect to depth. So, when is this considered to be small? Well, when z is less than 800 meters roughly, then if you plug in values of g and r g for air and T naught to be 300 Kelvin, you will find that this is small when z is less than 800 meters. So, when you are looking at applications, even if you assume air to be compressible, when the elevations are not large, then this linear variation in pressure with respect to the vertical distance is a very good one. So, we will stop here and we will continue in the next lecture. So, we will see you in the next lecture.